Now I want to discuss a couple of results that we can call patching lemmas. Okay, so the setting is like this. So f from x to y be a function between topological spaces. And we want to prove that it's continuous. Okay? And a kind of quite common way that maps like this might arise is we might define it sort of by cases. You might, in some sort of problem involving real numbers, you've got sort of one thing that you do when x is positive and a different thing that you do when x is less than or equal to 0, or you have one clause which is valid when t is greater than or equal to half, and a different clause that's valid when t is less than or equal to half, that sort of thing. So, so you want to understand how you can prove that a function is continuous when it's defined by cases in that sort of way. Okay, so let's suppose x can be written as some union of subsets like this. And we're going to give each xi the subspace topology as usual. And so that we can just take this map F that's defined on all of x and just restrict it to the individual subsets xi. So we're going to suppose that this is the let this be the restriction of F to xi. Okay. And then, so the first claim is so we can say that F is obtained by patching together F1 up to Fn, and the individual maps Fi are all continuous, so you might think that F has to be continuous. Unfortunately, that doesn't work in absolutely all cases. You do need some extra assumptions. And one possible set of extra assumptions is just that the sets xi are all open. Then F will be continuous. And suppose instead that x1 up to xn are all closed. And again, F is continuous. Okay, so this we can call open patching, and this we can call closed patching. Okay, so so why is this true? So let's write the proof of one. Suppose V contained in Y is open. And so we're going to put let's put U subscript I is Fi inverse of V, and it's easy to see that that's just the same thing as F inverse of V intersected with the set xi. Okay, but now as Fi is continuous, we see that Ui is open in xi, but xi is also open in x. Yeah, that's our assumption. We were doing case 1 here, where it's assumed that all the sets xi are open in x. And so that means that Ui is also open in x. Okay, so that was a proposition we had in the previous video. Okay, if you've got you've got a subset that's open, then then you go down to a further subset of that. Then the smaller subset is going to be open in the open set if and only if it's open in the whole space. Okay. That was a special property that we had with subspace topology on an open set. So that means if we take the union of the sets U1 up to UN, that's our kind of axiom B. Union of any system of open sets is open. So the union of these. But what is this union? That's remember, this was F inverse V intersect X1 okay, remember this UI is just the pre-image of V intersected with Xi, so we take the union of all those. But the union of these sets Xi was supposed to be equal to the whole of X. So the union of these guys here, these intersections, that's just equal to F inverse V. So F inverse V is open in X as required. That's what we had to do. Remember, V is we're wanting to prove that this is continuous, so we need to assume, give ourselves an open subset of Y and check that the pre-image is open in X, and that's what we've just done. So that's the proof of part 1. And the proof of 2 is almost exactly the same. But firstly, we just take this preliminary step. This is another proposition we proved a couple of videos ago. F is continuous if and only if the pre-image of any closed set is closed. Definition is that F is continuous if and only if the pre-image of any open set is open, but closed sets are just the complements of open sets, and so it's not hard to see that we have this alternative characterization. Show that something is continuous is enough to check that the pre-image of any closed set is closed. So we're going to let G be a closed set. And then I'm going to put Fi is pre-image under little fi of G, which is the same thing as the pre-image of G intersected with Xi. And note, Fi is closed in Xi because Fi is continuous. Okay. F lower I is continuous, G is closed in Y, so the pre-image under Fi of G must be closed in Xi. Let's just okay. So yes, okay. And then any finite union of closed sets is closed. I said that. That's closed in Xi, but Xi is closed in X, right? That was, so here we're doing case 2. Case 2, the assumption was that X1 up to Xn, they're all closed in X. So here we've got a closed subset of a closed subset, so that's closed in the bigger set. So Fi is closed in X. So we take F1 union up to Fn is a finite union of closed sets. Therefore closed. But F1 union of all these Fn's, that's easy to see from this description here. This is equal to F inverse G. So F inverse G is closed as required. So those are our two patching lemmas.